Okay, right. So hi everyone. I'm Joe, and I've partnered up with Sean this week for a duo special on defects, and this is part one of 2 tutorials looking at the sort of basic fundamentals that we need to understand defect chemistry and the properties that we can get from this and how it plays into the experiment. So a quick overview of what we're going to be looking at this time is shown on this slide. So at first, we're going to quickly talk about the importance of defects, the motivation for studying them, what materials they're useful for. Sean's then going to talk us through the different types of defects and the different sort of terminology. We're then going to look at how we can calculate formation energies and the theory behind that. And then we're going to look at transition level diagrams, which are basically our way of visualizing these formation energies. Then we're going to look at what we can take from these results, and finally how our theory can play into experimental observations of defects as well. And then next time, we're going to focus more on calculations, how to do them, what to put in your ring files, do's and don'ts, and sort of more practical stuff. So that'll be in a couple of weeks' time. So motivation. Essentially, defects control device behavior, quite simply. Whether it's in solar absorbing materials, as Sean was talking about last week, where you want to avoid charge carrier recombination of holes and electrons, or transparent conductors, touchscreens, that sort of thing, where you want to ride as many charge carriers which are generated by defects to the relevant band edges as possible, or in batteries where you want to see how lithium or sodium or potassium ions can sort of intercalate and de-intercalate into your systems, and to also look at degradation. The other side of looking at this as well is that defects are present everywhere, and you can't really look at anything without considering its defects because everything is defective. So there's like another side to it as well. Just give it a point. So, yeah. So now I'm going to hand over to Sean, who's going to start talking us through the nomenclature and some defects. There's going to be a bit of back and forth in this, so bear with us.
Okay, so there are a number of terms we use to classify and describe defects. So the first two, I suppose, overarching ones are intrinsic versus extrinsic. So intrinsic defects arise from the imperfect arrangement of the bulk atoms, or the atoms of the pure material. They're always present, and their concentrations can be controlled simply just with temperature. Extrinsic refers to defects arising from an external impurity, such as from doping, whether intentional or otherwise. Then on to the different kind of types of point defects we can have. So we can have either a vacancy, an interstitial, or a substitution. So a vacancy is just a missing atom at a lattice site. So for example, here where there's a missing cadmium atom at this point, you can have an interstitial where you have an extra atom located at an interstitial site in the lattice. So this is like a void in the crystal structure. For example, the octahedral or tetrahedral holes you can find in, say, zinc blende or FCC crystal structures. You can have a substitution. So this is an atom located at the lattice site of a different element. So a magnesium on an oxygen site, for example, or some other form of substitution. So these are often called anti-sites if they're an intrinsic substitution. So this can sometimes be a source of confusion with people. So they're referred to as an anti-site because it's one element located at the lattice site of the other. But typically, if we're talking about extrinsic substitutions, we just use the term substitution. And then you can have a complex, which is 2 or more point defects located near to each other, where there is some form of either elastic or electronic or magnetic interactions between them. Okay. So we usually use the Kroger-Vink notation for describing specific defects in materials, and it uses this form here. So X is the atomic species or the primary atomic species of the defect. So it's either the element that's at the center of the point defect, or if it's a vacancy, we just use a capital V, or in some cases, depending on the convention, a lowercase v. So things can get a bit confusing if you have vanadium.
Sean, normally you make a vacancy italic.
Italic as well?
Because so you don't mix it up with
vanadium.
Vanadium, yeah.
Okay. And so S, the subscript, is the lattice site at which the point defect is located. So this is either the elemental symbol of the original site. So for example, in this case, if we have a cadmium, a vacancy at a cadmium site, cadmium is our subscript because that's where that was the original element at that site. Or we use lowercase I for an interstitial site. And then finally, the superscript Q is the electronic charge of the species relative to the site that it occupies, or so relative to the original charge of that site. So Q is just the current charge minus the original charge. So, for example, in this case, if our original cadmium atom had a +2 oxidation state and now has an overall 0 oxidation state, we say that it's in the 2- charge state because it has 2 extra electrons relative to the original oxidation state. For the charge notation, there is a slight difference depending on convention. So the original Kroger-Vink notation, which is still used in a lot of chemistry papers, uses an X for neutral or 0, dashes for minus charge states, so for if it's negatively charged, or dots for a positive charge. Whereas in kind of material science, it's more common to see just the bare numbers, so 0, -2, or +2. Okay, and then I need just some quick examples. So if you just normal, so this wouldn't be a defect, but an aluminium ion on an aluminium site in a neutral charge state, it would be given by this. If you had a nickel copper anti-site, or if it was extrinsically doped to substitution, where again there's no charge difference relative to the original oxidation state, be given by this symbol here. So again, using the X for neutral. A vacancy on a chlorine site, and V, and then chlorine as the subscript. And this is in the singly positive charge state, so we use just 1 dot. And then finally, a interstitial calcium ion with 2 positive charges here. Okay, back to Joe.
Thanks, Sean. So now that we've got that under our belts, we can start thinking about defect formation energies and how we calculate these. So this is quite a crazy equation, but we can basically split it down into 4 parts. And I am going to talk about these 2, and then Sean will follow up and talk about these 2 afterwards. So the first term is this defect supercell minus host supercell equation, and this is simply the energy difference between a unit cell that has no defects in it at all, so the perfect host supercell, and then a supercell that has a defect D in any charge state Q, and it's simply the energy difference between these 2. So this is the first term, and there's not really much more to say about it than that. The second term is a bit more involved. You have to think about it a bit more, and it is this chemical potential term. And what it does is it essentially accounts for the change in Gibbs free energy when adding or removing an atom from your system. So if we look at this equation in the top here, N is positive for atoms. It's the number of atoms that you add or remove to the system. And N is positive for atoms that are removed from the host. It's positive because you are adding these atoms to an external reservoir somewhere else. And then if you are removing atoms from your host, it is negative. N is negative for atoms added to the host, because you are removing them from an external reservoir. Mu I here represents the chemical potential of your species, and I is the species itself. So that's all well and good, but we haven't actually discussed what this chemical potential is yet, which we're going to do now. So the thermodynamic definition is the rate of change of free energy of a thermodynamic system with respect to the change in the number of atoms in the system. So what this essentially means is it defines how the free energy changes as a contribution to a system changes. So it's summed up by this partial derivative here. So the chemical potential is the change in the internal energy with respect to the number of atoms in the system and constant entropy, volume, and having different atoms in the system. So the best way to think about this is in terms of an example. So here we would take zinc, oxygen, and zinc oxide. And these represent the only three stable phases in the chemical space of zinc, oxygen, and zinc oxide. And what we can do is calculate the thermodynamic stability of the host material, zinc oxide, by considering the chemical potentials of zinc and oxygen. We can construct this equation for the formation energy of zinc oxide, which is this term here, which is simply the product minus reactants. So the energy of zinc oxide minus the energy of zinc and oxygen. And that can be set equal to the chemical potential of zinc and oxygen. In terms of what we can calculate from DFT, the things that we can calculate and plug into this equation are the total DFT energies. So this will be our total DFT energy for zinc oxide, and this for elemental zinc and elemental oxygen. And note here that we're using E for energy rather than H for enthalpy, because enthalpy has a pressure and volume term in it as well, which we're not considering when doing our DFT calculations. So we're going to stick with zinc oxide and run through an example, because this probably still is seeming a bit abstract. So sticking with zinc oxide, we have the formation energy from products minus reactants from our VASP calculation, that's shown here. So the formation energy of zinc oxide is minus 3.3 EV. Note how this is all done in energy per formula unit. So for zinc oxide, this will be the energy per one formula unit of zinc oxide, and this is per zinc atom, and this is per oxygen atom. We can then consider the two extreme situations that would limit the formation of zinc oxide. That is a completely pure zinc environment where there is no oxygen, therefore the chemical potential of zinc is 0, and then the opposite, where there is no zinc and you have a pure oxygen environment, and the chemical potential of oxygen is 0, and zinc oxide will then coexist between these two limits. And if we basically consider these two situations and set it equal to this equation in the middle, we can calculate the chemical potential of each species with respect to the other at those two limits. We can now consider what happens for a chemical phase space that has more than just the two elements of a single phase in it. So let's look at titanium and oxygen, and we can now see that there are two stable competing phases. So there's TiO2 and Ti2O3. We can then calculate the formation energy of each species as before. And then we can construct a simultaneous equation. So we can subtract 2 times the top one, subtract the bottom one from 2 times the top one to get our chemical potential of oxygen. And that gives us a value of minus 3.52 EV. And then to calculate the chemical potential limits of titanium for titanium dioxide, we can just simply plug the chemical potentials of oxygen back into the formation energy equation for titanium dioxide, which gives us these two limits. We could then do this for titanium Ti2O3 as well. And we can plot both of these sets of answers like this. So what this shows is that you have TiO2 stable from up here down to here, which represents the minus 9.14 chemical potential up here, to the minus 2.10 chemical potential here. And then at this point, titanium sesqui oxide Ti2O3 becomes more stable and is now the dominant competing phase as you approach the completely Ti-rich conditions. I've taken these values in this example from our group page on this, which was written by Ben, so thanks, Ben. We can now consider, it's quite involved, it's quite a black story, but we can now consider how this plays back into our chemical potential term. So for a titanium vacancy, what we have done is removed one atom from our host, added one atom to an external reservoir, so our N is +1, and then we simply have that multiplied by our chemical potential for titanium, which we just calculated. And then we can then apply the same process for considering external dopants as well, but we now have to confine this within the chemical potential limits that we just calculated for our host material. So again, I will take the example that Ben's put on the wiki and work through that and talk us through it. So we can stick with titanium dioxide and imagine that we are doping it with niobium. We have 3 stable competing phases of niobium and oxygen, and the formation energy of each of these has been calculated in the exact same way as before. Now we can calculate the chemical potential of niobium by subbing in the chemical potential of oxygen under both Ti-rich and Ti-poor conditions. So we're just solving this equation for the 2 different values of oxygen chemical potential. Here we can see that under Ti-rich conditions, the most stable niobium containing phase is NBO, and under Ti-poor conditions, the most stable competing phase is NB2O5. And this makes sense if you think about it intuitively, because under Ti-poor O-rich conditions, you have loads of oxygen in the system, and you have a 5:2 ratio of oxygen to niobium here, whereas as you go into oxygen-poor conditions, you have a simple 1:1 ratio. So this all makes chemical sense if you think about it. So now we've calculated our chemical potential of titanium, oxygen, and niobium within the chemical potential limits of titanium oxide. We can then plug this back into our equation as well. So for a substitution of niobium on titanium, we need to consider, again, removing one titanium atom from the host and adding it to the reservoir. So we have our positive titanium here again. And now we need to also consider adding one niobium atom to the host and removing it from the reservoir. So we have a -1 here for the niobium and then the chemical potential as well. So this is how we would calculate the chemical potential term for a couple of different examples. Yeah. I'll now hand it back over to Sean to talk about the next 2 terms.
Okay, thank you. So next term in the formation energy equation for a point defect is this term here, which is the charge of the defect multiplied by the Fermi level in the material. So if we remember the kind of thermodynamic definition for what the Fermi level is, so the Fermi level of a solid state body is the thermodynamic work required to add 1 electron to the system. So as such, the Fermi level can be considered to be like a hypothetical energy level of an electron in the material, such that at thermodynamic equilibrium, this energy level would have a 50% probability of being occupied at any one time. So we can sometimes, or we can think about this in terms of the Fermi function in the material, which describes the occupancy of electronic states in the material. And so the Fermi level will correspond to the position of 50% occupancy of the electronic states. So as such, it represents the energy of the electronic reservoir of the system in the same way that the chemical potentials represent the energy of the atomic reservoirs. So as such, the Q times the Fermi level will give the energetic cost of removal or addition of electronic charge to the defect site from this charge reservoir of the system. Importantly, it is this term in the formation energy equation which gives rise to the Fermi level dependence of defect formation energies, which you'll see in the coming slides. So, for example, a defect in the positive charge state will increase in energy as the Fermi level increases. So if Q is positive, as Fermi level, as EF increases, the formation energy will increase. And we can understand this behavior by recalling the fact that the Fermi level describes our occupancy of electronic states. And so the electronic states associated with the defect are more likely to be occupied as the Fermi level moves up through the band gap or increases in the material. And so this becomes unfavorable for positively charged defects. And so this is why their formation energy increases. And we have the vice versa behavior for negatively charged defects. Okay. The last term in our formation energy equation, this here refers to finite size corrections, which we apply ex post facto, or like we apply retroactively to our calculations, which remove the unphysical or spurious defect interactions which are associated with the finite size of our simulation supercell. So due to the rapid increase in computational demand as we increase the number of atoms in our simulation cell, so represented in these blocks here, if we imagine this is our simulation supercell in DFT, we can't use a infinitely sized supercell due to this rapid increase in cost. And so we have to make a pragmatic choice where we make a supercell which is large enough to avoid any kind of elastic or structural interactions, or any, at least of any significance, between the defects in the different supercells. So i.e. the coordination environments, for example, of the bulk atoms at the edge of our supercell should not be significantly distorted by the presence of the defect. However, unfortunately, the Coulomb charge interactions are quite long range, and so we would need enormous supercells with thousands and thousands of atoms to avoid defect charge interactions. So what we do instead is we model the energy of these sort of charge interactions that would happen, and we then use this to predict the energies of these charge interactions, and then subtract this after the calculation to attempt to remove these effects from our formation energies. So essentially, these help us go from the picture of a low concentration impurity, so where you've like a defect in 1 in every 50 or so atoms, which is what our kind of supercell essentially corresponds to, and brings us from this picture to the case of isolated defects where you've 1 in a million or even lower concentration, which is what we are typically modeling experimentally. Okay. Yeah, so Joe is now going to show us how we kind of represent this visually using our defect formation energy diagrams.
Thanks, Sean. So yeah, now that we have sort of talked through each of the individual components, we can now start to build up a transition level diagram. So the eagle-eyed amongst you would have found a sort of vintage David Scanlon presentation on the Dropbox about how to read these, and how they work, and how to do the calculations. A few things have changed since then, so we're going to refresh it and go through here from scratch. So the first thing that we have is along the x-axis, we denote the Fermi level, which would typically range from the valence band maximum at 0 here to the conduction band minimum at this end. And then on the y-axis, we have the formation energy of a defect. And to construct this, we simply look at the y equals mx plus c relationship of our formation energy equation. So what we have is y is our formation energy here, M is our gradient, which is our charge state, as Sean was alluding to earlier. X is our Fermi energy, and plus C is all of this other governs sort of correction and the total energy difference and that sort of stuff. So let's just put some defects on here and we can sort of see how this plays out. So we can imagine that a positively charged defect with a Q of +1 will then have a positive gradient and form something like this. A neutral defect with a gradient of 0 will obviously have a horizontal line across the middle like this, and any negative defects will have a negative gradient like this. And say you have a -1 like here, a -2 would have an even steeper gradient going like this. When you put all of them on the same diagram, they obviously intersect, and we can solve these transitions by simply solving how to intersect two straight lines. So setting the two equations for y equal to each other, and then finding the common crossing points. And what these crossing points mean is they are the thermodynamic equilibrium points between the two charge states. So in this section here, at these Fermi levels, the +1 charge state is stable. Once it reaches this Fermi level here, you then have an equilibrium between the +1 and the neutral charge states being thermodynamically viable. And then as you increase the Fermi level further, you now find that the neutral charge state dominates. And then this again transitions here. So now that we sort of understand what the different directions mean and how the different charge states are represented on the diagram, we can now start to add some detail. So the first thing that we've done is constructed a diagram that shows the +1 and neutral charge states of a defect. So here and here, relative to what I'm now calling the conduction band edge, denoted by orange here. This is an N-type defect. This positive defect is an N-type defect, which means it has given up an electron. So it's donated an electron into the host material, which is now why it is in a positive charge state. We can see that the +1 state is stable up until around here, around 0.4 eV below the band edge. And this means that there is an energy gap of around 0.4 eV between the defect state and the conduction band minimum. And if you were to draw this on a band diagram, this is what you see. So the defect state lies here, and then there is this energy gap which corresponds to this on the band diagram. And when you have such a large energy gap as this, we call it a deep defect. And this is because the energy is not crossable at room temperature. So to populate to move an electron into the conduction band from this defect state, it won't have the room temperature. It needs some sort of associated activation energy. Deep defects are, well, what this diagram shows is a schematic of the effects that deep defects can have on electron hole recombination in solar cells. So we have our conduction band here at the top, our valence band here at the bottom, and a deep defect state in the band gap here. And by acting as a center at which holes and electrons can recombine, deep defect levels can be severely detrimental to solar cell efficiencies. In fact, they are the primary performance limiting factor in emerging photovoltaic materials. We now consider a case where this transition level diagram, where this transition level, lies closer to the conduction band edge, as is shown here on the band diagram. So this transition level is denoted by this defect here. And now it is easier for this charge carrier, this electron, to donate into the conduction band because there's a much smaller energy gap. And if this energy gap is within kBt, so Boltzmann constant times temperature of the band edge, then this can be thermally excited. And this situation is what we call a shallow defect. We can now consider when the transition level lies within the conduction band, so the +1 state is stable within the conduction band minimum up to here. And this is what we call resonant. This defect would be resonant. So there is no energy required for the conduction to occur. So there is no sort of activation energy for the electron to be donated into the conduction band, it can simply just drop down into the conduction band. And what we can tell from this is that we would expect very high levels of conductivity. So for deep donors or deep acceptors, we would expect some sort of activation barrier for conductivity to occur, whereas for shallow and resonant donors, like I've said, we can easily see charge carriers populating the valence and conduction bands respectively. And the final thing that I'm going to discuss before handing back to Sean is the dreaded chemical potentials again, and how these affect defects. So the formation energy of a defect is directly influenced by the chemical potential limits that we spent quite a while discussing earlier. And hopefully now this will make it a bit easier to understand. So if we concentrate on this red oxygen vacancy here on this left-hand diagram, which represents oxygen pore growth conditions, it's quite easy to form, the formation energy for an oxygen vacancy is quite low under oxygen pore conditions. And what this means is that when you're trying to grow a material in conditions with relatively low levels of oxygen, it's quite easy for an oxygen vacancy to form because there's not much oxygen in the system. If you now calculate the formation energies of this under oxygen-rich conditions, so you're pumping the growth chamber full of oxygen, it now is much harder to get oxygen vacancies because there's just loads more oxygen in the system. So this shows you how the formation energy of defects can be significantly altered by the growth conditions that you grow your material in. So now I will hand back over to Sean to talk about some other insights that we can get from transition level diagrams. I'll mute myself now.
Thank you, Joe. So, yeah, one of the main points that we can take from our defect formation energies is we can use it to predict the equilibrium concentrations of defects in our material. So as we mentioned earlier, that for intrinsic defects at least, they are always present in materials in some concentration, which is a result of our good old friend thermodynamics. So at thermodynamic equilibrium, the Gibbs free energy is minimized. So in this case, represented by delta F. And this is given by the enthalpy minus temperature times the entropy. So for a point defect, the primary contribution to entropy in this case is configurational entropy, which is given by this formula here. So entropy is equal to K Boltzmann, Boltzmann constant, times natural logarithm of the multiplicity of the system. So we can think about this by picturing a lattice of point sites. And if we create a vacancy at one point in this lattice, we now have many points where this vacancy can occur. So many equivalent configurations where this vacancy could be located. And so this is what we mean by multiplicity. So it's the number of possible arrangements of the defects in the material. So this being our degree of freedom in this case. So we can see that as we increase the number of defects in our material, this the multiplicity, so the way that these defects can be arranged, will also increase. And so there is the minus term here means that this entropy boost can lower the free energy in the system when we form a certain number of defects. However, due to the logarithmic form of this term, the contribution or the entropy increase starts to bottom out as the gradient decreases as the defect concentration increases. And so as the defect concentration increases, this entropy has less and less of an effect on the free energy of the system, or less of a gradient anyway. The enthalpy, on the other hand, refers to the formation energy of the defect. And so this is pretty much always positive as we are breaking bonds by forming the defect. And so, of course, this term will increase approximately linearly as the defect concentration increases. And so at some point, we will have a minimum where the Gibbs free energy is at its equilibrium or minimum position. And this is our point of thermodynamic equilibrium. And this is the and so the concentration of the defects at this point will be the kind of thermodynamic equilibrium of the system. If you do the maths, you end up with this formula here, which gives you this defect concentration that corresponds to this point, where the defect concentration is equal to the concentration of the lattice sites at which the defect can occur, times the negative exponential of the enthalpy, so in this case the formation energy, over the thermal energy, so K Boltzmann times temperature. So how this essentially relates or translates to our transition level or defect formation energy diagram. So Joe made this nice figure, and that kind of essentially shows that the lower the line on the formation energy diagram, the lower the formation energy, because that's what our y-axis is on these diagrams. And so the higher concentration we expect for that defect in that charge state at thermal equilibrium, at least. So in this case, the light blue line here should give a much higher concentration than the dark blue line, so for the defect it corresponds to, due to this exponential dependence of the defect concentrations on the formation energies. That said, out of equilibrium conditions can also occur. For example, when crystals are grown or annealed at high temperature before being quenched to room temperature or lower, or another example is during solar cell operation, when defects can trap excited electrons or holes and thus change charge states from their equilibrium charge states. So another thing that defect formation energies help us to determine is the self-consistent Fermi level in a material. So in a semiconductor at equilibrium, the charge neutrality condition is maintained, where the total number of positive holes in our valence band plus the number of positively charged defects or donors is equal to the number of electrons in the conduction band and plus the number of negatively charged defects or acceptors. So if we imagine, in this case, kind of a simplified picture with just this single defect with 3 different charge states is present in our material, and our Fermi level was at this position, we can see that we would have far more of the positively charged defect than the negatively charged defect present in the material, because at this Fermi level, the formation energy of the positively charged defect here is much lower than that of the negatively charged or negative charge state. And again, remembering this exponential dependence of the defect concentrations on formation energy, we can see that we will have far more of this defect present in the material. On top of that, the Fermi level being slightly closer to the valence band than the conduction band also means that we'll have a slightly higher concentration of thermal holes at the valence band than thermal electrons at the conduction band. And so in this case, our charge neutrality condition wouldn't be maintained if this was the kind of sole defect in our system, as both of these terms are now larger than the terms on this side. Likewise, if our Fermi energy or Fermi level was up here, we'd end up with more negatively charged defects. Again, its formation energy being lower at this point, and also more thermal electrons because we're now closer to the conduction band minimum. So the result is what we call a self-consistent Fermi level, where the Fermi level will adopt a position at which this charge neutrality condition is satisfied. So in this case, it occurs right at the intersection of these 2 points, so that we have an equal concentration of positively charged defects, an equal concentration of negatively charged defects. We'll also have a quite large concentration of the defect in the neutral charge state. However, this won't affect the position of the Fermi level, as it doesn't affect our charge neutrality condition. And then also being at mid-gap, it's going to have an equal concentration of thermal electrons and thermal holes. Of course, this behavior becomes a bit more complicated with more defects present, but the overall concept and behavior is the same, with the competing formation of the low energy defects. So for example, these 2 negative charge state defects and these positively charged defects compete there. So their competing formation will determine the overall position of this self-consistent Fermi level in the material. Okay. So looking towards some of the material properties that defects can influence, one of the most important in many cases is the optical behavior. So the presence of defects in a material can affect the absorption and the emission of materials, both in useful ways. So for example, defects are often used in many laser applications, or in harmful ways where they can quench the emission of LED materials. So to understand this behavior, it's useful to visualize the defect in what we call a configuration coordinate diagram. So all this is just the potential energy surface of the defect in its different charge states, where the x-axis is some structural coordinate along the path from the relaxed structure of the defect in one charge state to the relaxed structure of the defect in the other charge state. So in this case, this point being the relaxed structure of the single negative vacancy, and this position being the relaxed structure of the negatively charged, double negatively charged vacancy. So for example, in this case, the double negative charge vacancy has a perfect tetrahedral arrangement, whereas the single negative vacancy has a C3V symmetry, so 3 equivalent tellurium neighbors to the vacancy and 1 atom at a longer distance away. And so this x-axis just refers to the path between this and this structure. So this is analogous to the reaction coordinate used in chemical reaction diagrams that you may have seen in catalysis courses, for example. So if you recall the Frank-Condon approximation, which is itself a result of the Born-Oppenheimer approximation, or if you don't know what that means or who those people are, they basically state that electrons move much faster than atoms. So this means that if a defect is optically excited, i.e. if it absorbs energy from a photon, it can emit an electron or a hole and change its charge state, but that this process happens faster than the ions can move. As such, the optically excited state is the defect in the new charge state, so in this case, in the -2 charge state with a hole emitted to the valence band maximum, but still in the structure of the relaxed -1 charge defect. So using these diagrams, we can calculate the energy of absorption or emission, as well as the line shape of these spectra, though this typically requires a larger number of calculations. We can calculate the Frank-Condon or vibrational relaxation energy from the optically excited state to the relaxed configuration, etc. Another way this behavior is often visualized is via a transition level diagram, where, as well as showing the normal kind of equilibrium formation energies of the defect in its charge state, so that would just be the blue highlighted lines here, we also show the formation energies of the defect in the relaxed structure of the other charge state. So that's what the big or represents here. So in this case, we have the this is just the formation energy of the neutral defect in the relaxed configuration for the neutral defect. But up here we have the formation energy of the, again, the neutral defect, but in the relaxed configuration of the -1 charge state. And same here for the -1 charge state, but in the configuration of the neutral defect. And so the intersection of these lines with the original formation energies are known as optical transition levels. And the separation of these optical transition levels with the band edges corresponds to the energies of absorption and emission for this defect. Okay. So I'm going to give it back to Joe, who's going to talk to us about some other experimental techniques that we can compare to for defects.
Yeah, thanks, Sean. So I'm going to now talk about one experimental technique that we can use to look at defect charge states, and that is HAXPES, or hard energy X-ray photoelectron spectroscopy. So if we first focus on the left-hand side of this figure, it's the same transition level diagram that I showed you earlier, where we looked at the oxygen valency. But now we're going to consider these two cerium on indium defects. So what we have here is the cerium sitting on an indium site in the +1 charge state. So what this represents is a cerium oxidation state 4 atom. Oh, God, Siri's getting excited. That is a cerium in the oxidation state 4 sitting on a indium on oxidation state 3 in indium oxide. And then it transitions to a cerium oxidation state 3 atom sitting on an indium oxidation state 3 as well. So it goes from 4+ to 3+. And then what we have on the right here are two different XPS spectrums of a cerium-doped indium oxide film, one at a very low concentration and one at a very high concentration. And what these basically represent are two different snapshots of two different Fermi levels. So at the low doped cerium indium oxide film, this represents a situation down here, whereas the more heavily doped cerium indium oxide film is at a higher Fermi level. So if we look at the low one first, we have an 86% contribution of states in cerium oxidation state 4, which are these red peaks here, and a 14% contribution from states in cerium oxidation state 3. As we then move to the higher Fermi level, so further along the x-axis here, which corresponds to the more heavily doped system, we now see that we have only a 57% contribution from cerium 4 and a 43% contribution from cerium 3. So what this shows us is that as we move up the Fermi level, we now transition to the neutral cerium defect, the cerium 3, and this is reflected in seeing more cerium 3 in our XPS. So this is a really neat way of seeing how your different charge states play out at different Fermi levels. Another experimental technique that can be used is Dlts, which is deep level transient spectroscopy. And it's a technique that emerged in the 70s that allows you to observe charge carrier traps near the valence band and conduction band minimum. So how it works is you pulse a system. I'm getting an echo. Has someone got their mic on? Thanks. So you send a voltage pulse into your system, and it reduces the electric field in a region, causing free carriers to penetrate this region and saturate any defect sites that might be there. After the pulse, the defect sites then emit these carriers again via a thermal emission process. And then this process can be measured at different scanning rates and at different temperatures to basically build up a profile. And this is what we see here. So we see that we have one defect site with an activation energy of about 0.44 eV and one at 0.76. And these are positive on the y-axis, so these are whole sites. These energies can then be compared with the transition levels and a defect transition level diagram. So I'm going to show this here. And by modeling the transition level energies to include a temperature dependence, we can draw comparisons between the two. So this is the transition level diagram for Cu2O from David back in the day. And what he's done is he's looked at the copper vacancy in the system and a split copper vacancy in the system. So this is basically just two ways of forming copper vacancies. And the transition levels for these are denoted by the circles. And then these two dotted lines represent two signals from Dlts experiments that correspond pretty much bang on to where these transition level happens. So yeah, here we have a really nice agreement between the transition levels calculated from DFT and what we can observe from whole generation experiment. So I think that's it. We can now quickly think about what we've just looked at and what we're going to look at next time. So we've basically summed up all of the different types of defects that you can see and some potential applications of and analysis. And then next time, we're going to look at how we can consider more complicated chemical potential spaces. So way back at the start, when we were looking at titanium dioxide, we can now consider what would happen if we, say, have a ternary system rather than a simple binary. We're also going to look at how to set up some defect calculations. So the actual sort of nitty-gritty, setting up in-cars, using automated workflows, all that sort of stuff. We're going to look at how the finite size corrections play out in practice. We can look at polar charge density to see how these defects have sort of local effects on the system. And we'll also look at optical transitions in a bit more detail if we've got time as well. So I'll just leave a final slide up of some recommended further reading if you're interested. So this first is a paper by Lani and Zunga, who basically came up with most of the post-processing corrections required for defects. The second is a review by Freyzold and Van der Walle on basically how defect calculations from the beginning into where we are, or to where we were in 2014. Then there are two papers by Ben and David on different types of dopants, so resonant donors in indium oxide and tin oxide. And then there is a final paper here by Van der Walle and co-workers on how DLTS interplays with with transition level diagrams. And then there's a final book here as well, Advanced Calculations for Defects in Materials, which is quite a good read as well. So there we have it. I think that's it. I just want to thank, oh, no, there's no bonus content, sorry. I just want to thank Sean for helping me write this, and we're open to take any questions.
Thank you very much, guys. That was certainly, I'm just jumping in because David's just gone, I think. That was certainly the clearest explanation of defect chemistry in 1 hour that I've ever seen. So yeah, really nice. I'll start with just one question. So you mentioned like defect concentration levels quite a lot at different points. Have you got any, could either of you comment on sort of what typical intrinsic defect kind of concentration levels might be in some example systems, or like what the units are, because just so that people know kind of what they're looking out for.
Do you want
Yeah. Do you want to take this, Sean? Or do you want me to go for it?
Yeah, I was talking about concentration. I'll take this one. So the thing is, the concentration range can vary massively, again, because of this exponential dependence on the formation energies. And so the concentration at which a defect kind of becomes significant in a material also...
You're back. Okay, yeah, give it another go.
Maybe they're just acting. Yeah, so if in a material like gallium arsenic, for example, which is typically grown at very high purities, even a kind of relatively small concentration of defects can have a significant impact, for example, on charge carrier recombination. So firstly, the units we use are usually centimeter per centimeter cubed, so centimeters to the -3. And so the bulk atoms themselves in a material are usually somewhere in 10 to the 20, kind of mid 20s, I think, if I'm correct. So like kind of around 10 to 24 to 10 to 27, depending on the atoms is kind of the concentration of the bulk atoms. So then defect are generally somewhere in the range of kind of 10 to the 18, 19 for a very high concentration defect, where you're kind of more talking about like doping there rather than kind of just isolated defects. But this can be all the way down to 10 to the 1 or 10 to the 2, which you'd kind of say that's a very extremely low concentration that won't have any sort of noticeable effect in the material. So the kind of range at which defect concentrations can be measured and that their effects can be kind of witnessed in the material is probably around 10 to the 10 to 10 to the 20 centimeters to the -3. It's kind of ballpark range.
Great, thank you.
Nice. Take it away.
Okay, you can see my screen on Zoom.
Oh, still loading. Yeah.
Yeah, it says your screen sharing is paused. Resume share. Okay. Yeah. See. Now?
Yeah.
Cool.
Brilliant. Cool. Take it away.
Okay. Right. So, I guess I was going to do the intros to who I am as well, in case there's any new people here. But I think, judging from who's on the Zoom call and who's in the room, I think everyone knows me. But yeah, I'm Sean. Finished the third year of my PhD now in the group, so going into fourth year, and I mainly work on defects and solar cells. So yeah, I'm going to talk about shaking and breaking. Actually, pause. It gets annoying after a while. So talking about defect structure searching. So apologies to some of the people who were in the GRC. You will have seen some of the slides from today. Go on to what the outline is. But to a lot of other people in the group, I guess people have heard mentions of this shake and break or kind of defect distortion approach. But I don't think I've ever actually presented at the group meeting. I know Araya presented some while this project was ongoing over a year ago. But yeah, kind of to present some of the finished product and what the ongoing developments and outlook is for this method. Okay, so yeah, I'll just start by giving basically an introduction to what the method is, or what we're kind of talking about when we say shake and break or the bond distortion approach. Some example cases of its use, then an outlook for where I think it could be extended or improved, and encourage any sort of feedback or insights from people on that, if people have thoughts as to some potentially successful ways in further developing it, and then kind of briefly mention some ongoing developments, or basically kind of pain in the holes of PyMatGen making breaking changes and trying to do some other things as well. Okay. So yeah, to start, I'll kind of just give a reminder of the widely used supercell approach, which is what we use when calculating defects or point defects in solids. So what we do is we start with our relaxed crystal structure of the host materials, or a host primitive cell that we've relaxed and determined the equilibrium lattice constant. From this, we then generate a supercell of the crystal, which is large enough to avoid significant defect interactions between neighboring periodic supercells. And then with this supercell as our base, we go on to generate the different defects we want to calculate. So for example, here we can make a vacancy by just removing one of the atoms in the center. For anti-sites, what we do is we place one of these red atoms on a blue atom site, or vice versa. Or for interstitials, we'd start placing atoms in high symmetry sites in between the atoms, or in the interstices of the material. So we then allow the structure to relax using DFT, most likely, or some other computational method, which gives us our final defect structure. And then from this defect structure, we can calculate all the properties we might want to know for our defect. So this can be, the formation energy, which in combination with the structure gives us all these other properties. So the resulting defect concentration in the material, the transition level position, whether it's deep or shallow, its doping behavior, capture of electrons or holes, diffusion, catalytic activity, etc. So basically, from the structure of the defect, we derive all properties that are then associated with that defect species. Okay, so kind of with that sort of approach there, sort of workflow, it all looks relatively simple so far. Well, is a kind of key issue that misses, that is what ShakeNBreak is about, or what it's trying to combat. So when we generate our initial defect structure this way, so for the vacancy example, I said we just remove a vacancy and then use VASP to relax the structure from there with a geometry-based optimizer, or a gradient-based geometry optimizer. There's no guarantee that it will actually give us the true ground state defect structure. So for example, this ideal undistorted defect structure could actually lie much closer to a local minimum on the potential energy surface, as shown here, which would then give us a higher energy metastable structure, which does not reflect the true ground state defect structure, or true defect behavior, which would be this structure over here. So a question we might ask is, well, how prevalent is this behavior? Is it a common occurrence for defects in solids where a standard approach misses the true ground state structure, or is it just a common occurrence, or is it just a rare behavior for some specific defects? So in Araya's master's project, we tested this. So we applied kind of a structure searching method that we were developing as the project was going on, to a wide and diverse range of materials. So see here we go all the way from silicon, kind of the classic example, and covalent semiconductor, to 2 6s and 3 5s, more kind of emerging ionic covalent materials, as well as very ionic materials, or oxides over here. And we found this behavior to occur for defects in every one of these materials we tested, where you get these energy lowering reconstructions of the defect structure that are missed by the standard defect modeling procedure I just described. So looking closely at the reconstructions we observed, we could see that there was a variety of underlying chemical effects which can drive this reconstruction behavior. So for example, in certain materials, you have a dimerization, which is where two atoms near the defect can come much closer together and form a dimer type bond, and this can greatly lower the energy of that defect. In other cases, you can get some sort of rearrangement that reduces the number of unfavorable cation-cation or anion-anion bonds, where you have a bit of repulsion, and maximizes the number of favorable I call hetero-ionic or cation-anion bonds. So for example, here, where this gallium can displace off-site and then get this extra gallium-arsenic bond here. In other cases, particularly for a lot of the ionic materials you look at, you see that it's due to the effects on either the crystal field splitting of the d orbitals in an octahedral or tetrahedral environment, and or Jahn-Teller effects. So the effect on the electronic levels of the defect and how that can lower the energy. So here again, this distorting of the high symmetry site of this palladium to this site here lowers the energy through its effect on the electron energy levels. And then lastly, in some cases, you find that it's essentially just driven by electrostatics, where you get some sort of rearrangement that doesn't necessarily constitute a change in the number of bonds of the at the defect site, but just means that the atoms are placed so that you minimize Coulomb repulsion between similarly charged species, so between cations and cations or anions and anions, and maximize Coulomb attraction between cations and anions, so oppositely charged species. Okay, so to give kind of just a quick representative example of one of these reconstruction subclasses we observed. So this dimerization I mentioned here, that can happen. We find that this happens for the cadmium vacancy in cadmium telluride, which has kind of been our go-to example, just because some of the behavior is very relatively simple to analyze. And so we find that basically there's this initial barrier to two of the atoms coming closer together. So initially these two tellurium, if you move them closer together, there's a barrier to this, and the energy increases, and they don't like doing this. But after you go past a certain point, they start to bond with each other, and this greatly lowers the energy. And then you can get to this ground state structure here, where two of them have moved very close together, like 2.5 angstrom, and form this dimer bond that compensates a lot of the dangling bonds that are formed by the defect. In this case, we find that it qualitatively alters the electronic behavior of the cadmium vacancy in cadmium telluride. So it changes it from having 2 transition levels to just 1 deep negative U level, and also affects the recombination behavior, or qualitatively affects the recombination behavior, which I'll show later on as well. Okay, so yeah, now that we've established this is a common phenomenon in solids, the next question we might ask is, well, how important can this behavior be? So if we remind ourselves that all these properties are essentially derived from the defect structure when we calculate it, and see that having the wrong structure can give you incorrect properties here, and so this can greatly affect whatever predictions you're making for your material or for the defects in that material. So one kind of nice representative example is maybe the antimony vacancy in the antimony sulfide and selenide, where we find pretty significant energy lowerings of up to 2 electron volts when you apply a method to this defect to see, is your unperturbed defect or relaxation actually giving you the true ground state. And you can see that this qualitatively alters the transition levels in this material, and for such a large energy change would actually constitute up to like 20 orders of magnitude in the difference in concentration of that defect species in your material. So again, that's due to the exponential dependence of defect concentration on the formation energy. So yeah, the small changes in the formation energy can have pretty significant effects in the actual concentrations that you're predicting in the material. So as I mentioned earlier, one of the other key changes when you have a change in the defect structure, regardless of what that actually does to the formation energy or transition level, is also how it affects the carrier capture behavior. So this is the process of a defect capturing electrons or holes, for example, in a solar cell under operation. And this is actually kind of the key limiting factor in most solar cell technologies, this defect-mediated recombination behavior. And so essentially these diagrams describe the recombination behavior at point defects in semiconductors. So I won't go into detail explaining what it's really showing here, but the key point is that on the left here is with the ground state defect structure that we find with ShakeNBreak. On the right is the metastable structure you get from a standard relaxation. You can see that the potential energy surfaces look completely different in the two cases, and the resulting prediction of how fast hole or electron capture is just swaps. So in one case, you find that hole capture is quite slow, but electron capture is very fast. In the other case, you find the opposite conclusion. So this is kind of showing how important getting the correct defect structure can be, particularly in the case of, say, solar cell materials, where you're calculating these properties where it's not even its effect on the formation energy or concentration. That's the key difference here. So yeah, some further examples of where this behavior has been noted and found to be crucial are listed here. And so it's been found by many other people, not just us. and even as far back as 2004, this Lanny Zunger PRL was kind of one of the big ones, or initial sort of realizations of this behavior for defects in semiconductors. So I guess the initial key example in our field was maybe the DX centers in silicon and gallium arsenide, where people started noticing that if you displaced some of the atoms significantly off-site, you got this much lower energy defect, what we call a DX center, and explained some kind of long-standing puzzling observations in these materials. So things like persistent photoconductivity, for example. And then, I guess the Lanny Zunger was kind of the next big one, because the DX centers were maybe back in the 80s or 90s where that was realized, where they found this behavior in a range of 2-6 semiconductors, and found that it explained kind of, again, previously puzzling observations of color centers and deep anion vacancies in these compounds. But it's been noted in quite a range of different materials and affecting a range of different properties. So from doping to catalytic activity, persistent photoconductivity, defect absorption and band gap lowering, etc. Okay, so I'll kind of briefly discuss some of the alternative structure searching approaches that have been proposed in the literature, and what maybe their advantages and disadvantages are, and maybe if some of what works for them could be also incorporated into our method. So one approach to deal with this behavior is the so-called electron attractor method, and this from the mainly discussed at a group of Pham Deskins, but it's been around for quite a while. And essentially what you do is you manually replace your defect atom with a more or a less electronegative element, depending on the charge state of your defect. And this enforces charge localization at your defect site. So it either enforces that if you have an extra electron, that it localizes at that defect site, or an extra hole will localize at that defect site. So then you can relax this structure to get what we call a pre-converged structure, or essentially pushing your structure closer towards what you think anyway is the ground state minimum on your potential energy surface. And then with this pre-converged structure, you then replace this fake substitutional atom with your original defect atom, and relax from there, and hope that is kind of pushed you close enough to the ground state minimum on the potential energy surface to then give you that defect ground state structure. So while this works quite well for polaronic defects, it only really works for polaronic defects, defects that have a polaron associated with the defect site. It also requires quite a bit of manual effort and intuition or prior knowledge of the polaron site, and that you have to basically decide where the polaron is going to be for your defect, and then make these fake substitutions based on that. In doing so, it biases it toward a specific polaron structure, which may not actually be the true ground state structure. So, for example, in certain defects in some of these materials, we found that even though maybe there is a polaronic defect structure that's slightly lower in energy than the unperturbed defect relaxation, there's actually an alternative structure that's even lower energy than that, where you can have, say, a dimer formation or some other type of rebonding that's even lower energy. And so you would miss out on those in using this approach. Okay. An alternative approach is random sampling, where essentially you generate a wide range of trial structures by randomly placing atoms around the defect site with some minimum distance constraints before relaxation. So this can be a powerful method and is essentially guaranteed to find the ground state eventually once you've tested enough structures, which could be in the hundreds or thousands for each defect. But again, it requires quite a lot of manual effort and is quite inefficient. It requires many calculations, and so typically it's only possible with lower levels of theory, such as GGA, DFT, which we know will often just in the first place give incorrect defect structures. And so it's generally infeasible for our type of defect studies, where we look at a range of defects, or maybe all intrinsic defects in a material. Okay. So lastly, one other approach to mention is this evolutionary algorithm approach, which was recently proposed by Aragoni and Madsen, which is conceptually somewhat similar to the random sampling approach. So here you generate a range of trial structures from atomic displacements around the defect site. You calculate their forces and energies, and then use this data to mutate into new structures via an evolutionary algorithm before you repeat this until convergence, until you found what you think is the lowest energy structure. Okay. So while again, this can be a powerful method for identifying ground state and metastable defect structures, and can also be enhanced with machine learning models, it again requires a lot of manual effort in high parameter tuning for each defect species, and is somewhat inefficient, making it infeasible for our typical full defect studies. Okay. So in our method, what we do is to try and leverage the localized sort of molecule in a solid type behavior of point defects to try and efficiently navigate the structural potential energy surface. So to do this, we apply a range of distortions to the defect neighbor atoms, where the number of bonds to distort is set by the change in the electron count for that defect species relative to the bulk. So while this isn't perfect, it typically gives us a good starting point for the likely directions in which structural reconstructions could occur. And then from these distortions, we obtain a mesh of trial defect structures, which we then rattle, meaning we add some small random displacements to break symmetry, disrupting the lattice potential and essentially aiding in the location of the global minimum for our gradient-based optimizer. So we then relax these structures at a reliable level of theory, i.e. hybrid DFT, but using cheap, coarse numerical parameters such as gamma point only sampling and some other parameter choices, which makes the calculations run fast while retaining sufficient qualitative accuracy to identify distinct defect structures. So if we then plot these energies versus distortion, we can see that our ground state is obtained within a certain distortion range. For example, here the tellurium dimer ground state of the cadmium vacancy is obtained when we initially compress the neighbor bonds by 30% or more, and it then corresponds to these points on the potential energy surface. Okay. So in summary, the strategy here is to try and use a coarse exploration of the potential energy surface to identify the ground state structure before continuing with the final converged energy calculations with this correct structure. We found this method to be extremely successful in identifying structural reconstructions at defects and kind of in this wide and diverse range of materials here. We find that it also can work well to locate low energy metastable structures, which are also important for diffusion and carrier recombination in materials. And it works out to be relatively efficient, coming to typically less than 10% of the computational cost of a full defect study through our use of these kind of numerically inaccurate but qualitatively accurate parameters for you doing the structure searching. So yeah, just coming to the conclusions. So the main conclusions are that obtaining the correct defect structure is important, and you find that these energy lowering reconstructions are maybe much more prevalent than kind of we as a community have thought, and are present in a wide and diverse range of materials and for a diverse range of chemical effects. We find it's particularly common in cases of mixed ionic covalent bonding, where you have these soft, polarizable and anharmonic bonds, or low crystal symmetry or multinuclear composition, where you can find a lot of dimer formation and rebonding to occur. It also occurs quite a lot in ionic systems, and in these cases, it's particularly driven by large distortions from defects or dopants, or Jan-Teller or crystal field effects, or due to polaron formation. So ShakeNBreak is our method to try and combat this and aid the accuracy of defect calculations, but we're also kind of looking forward and thinking, how could it be further improved? To finish, I'd like to thank everyone who's contributed, whether actually developing the code, but also in terms of feedback through usage. So there's quite a lot of members in the Scanlon group who've used it and given very useful feedback from that. So I'd like to thank everyone very much. But of course, big thanks obviously to Araya, who is the master student who ran most of the initial calculations for this work last year, and she's actually going to be joining Aaron's group next year as a PhD student, which is pretty exciting. And her plan is to essentially follow up on some of this work and looking at more at the metastable configurations that we see. So yeah, so that took a while, but thank you very much.
Thanks, Sean, for a really enlightening and comprehensive sort of overview of what you've been working on. It's like really exciting stuff. And like you said, I think it really imposes just how relevant this is to pretty much all of the work that we're doing. Right. Hi, everyone. We're back again to talk about defects again. And this time it's going to have a bit more of a practical flavour to it with some sort of hands-on tips and tricks on how to set up calculations and what to look for and some just general guidance. So here we have a quick overview of what we're going to look at today. So I will start off by talking about the relationship between the primitive cell and the supercell. And then Sean will talk about how to actually create defects inside your supercell once you've made it. I'll then talk through some of the important in-car tags that you really need when doing these calculations. And then Sean will then talk about how to optimize these calculations using some like parallelization and other such things. He will then talk about the finite correction schemes that we looked at last time in a bit more detail and look at how these can affect your results. And then I'll round off by doing a small section on polarons and also looking at some chemical potential limits, but for some more complex systems and how to get around this. And then Sean will finish off by wrapping up. So let's begin. So you will typically start a defect study with your primitive unit cell. You'll do all your bulk calculations on because it's much cheaper and gives you all the information that you need. And in this case, I've just shown you the primitive cell of zinc oxide. To do a defect analysis on this, you need a much larger cell than the primitive cell, as Sean discussed a couple of weeks ago. You ideally want your supercell to be cubic, and you want to make it large enough so that you get minimal interaction between defects in neighboring cells. In the ideal world, your supercell would be as big as you can get it conceivably, but realistically, we are limited by cost and computational power. So generally, we tend to go for supercells in the sort of 70 to 120 atom range. And for this, we can still use more than one K point. But if you go to anything larger than that, then it just becomes increasingly more expensive, especially with hybrids. So it's not done so often. If you're unsure about how big to make your supercell, then you can do a test on a couple of different sizes, calculate a vacancy or like a defect just for one for each size supercell, and then see if your energies change too much. So to actually create a supercell from this unit cell, we can extend it by 3 and 3 in the A and B directions and 2 in the C directions to generate this roughly cubic supercell. How do we do that? Well, you can do it in one of two ways. You can use the old school superscript from the MA tools thing that you would have downloaded when you did your master's setup, and it's on everyone's system. Or if you're feeling a bit more modern, you can do it using the PyNightGen core structure module, which I think is the way that people tend to be going nowadays. One thing that you have to bear in mind when you move from your primitive cell to your supercell is the relationship between real and reciprocal space. So if you have made your cell bigger in real space, you then need to sample. It would then become smaller in reciprocal space. So you then need to change the density of your sampling with your K points as well. So an example here is, again, from the cell beforehand. So I had the primitive cell where using K-grid series, we would get a recommended K-grid of 8 by 8 by 4. And then by moving to a supercell, 3 by 3 by 2 supercell, you would then need to change your K-point grid to 3 by 3 by 2 to keep the same K-point spacing. we can apply this again if you had a 4 by 4 by 4 K points in a primitive cell, you would then you doubled it, you would then want a 2 by 2 by 2 K point grid in a supercell. So yeah, it's just one really important thing to keep in mind, is just to make sure that you are looking at a similar sort of K point density when moving from primitive to supercells. So I'll now hand over to Sean to talk about the next slide.
So the next question is how we go about creating the point defects in our simulation supercell. And so there are two main ways of doing this. So we can use the good old pen and paper, so manual file editing way, or as is becoming increasingly popular, semi-automatically through Python. Firstly, the general workflow, if you're doing kind of the manual way, is to look at your supercell maybe in Vesta first, or some other visualization software. Find the site at which you want to create a defect and get the fractional coordinates in the supercell of this site. You then manually edit the POSCAR with something like Vim or your favorite text editor, and you need to change a couple of things. So firstly, it's always a good idea maybe to change the comment line at the top of the POSCAR, so you know what it is. So just maybe a line saying what defect you're actually making in this POSCAR. The number of atoms, so down here you need to change corresponding to what's happening. So if it's a vacancy, you'll have to reduce one of the numbers by 1, or for anti-sites or extrinsic substitutions, you might have to add something. And then you need to change the positional coordinates down here. So do be aware that you need to be careful as to which coordinates correspond to which atom. So the POSCAR positional ordering corresponds to the order you give here. So the first 4 lines in this case would be the tin atoms, the next 2 would be antimony, and so on. So for a vacancy, it's generally quite simple. So you literally just have to remove the line that has the coordinates of the atom site at which you're creating a vacancy. For something like a substitution, it means moving the coordinates so that the position corresponds now to an atom of a different element. Or for an interstitial, it would mean adding a line with the new coordinates or with the coordinates of the interstitial. Okay, and yeah, so it's always good to maybe sanity check at least 1 or 2 of these defect POSCARs by looking at them in Vesta or Crystal Maker and checking that they look like what you think it should be. So it's showing the vacancy or substitution that you think you've created in this POSCAR. Click. So the alternative and typically less painful and less error-prone method is to generate our defects using Python. So there are a few Python packages now that offer different ways to do this, such as PyCDT, PyLADA, etc. But a bit of shameless promotion, I've developed a package that relies on some of the functions from these other packages and essentially streamlines a lot of this and has a lot of extra features, particularly around setting up and analyzing VASP defect calculations, and gets around a few sticking points with these other packages. So with just a couple of lines of code, you can generate all the intrinsic defects as well as specific extrinsic defects in your system. So there's an example workbook on the GitHub repo, and more documentation will be added when this undergoes some proper development. But to give a kind of general outline of the workflow involved. So firstly, you just load your bulk structure, whether you can do as the primitive or already generated bulk supercell. You then feed this into the charge defect structures Python class with arguments specifying things like the maximum number of atoms in your supercell. So this is just if you initially fed it a primitive structure and then wanted to kind of get it to generate your supercell for you. You can specify specific extrinsic substitutions. So in this case, saying that you want to allow the selenium on tellurium substitutions. Just some other flags as to kind of to include or exclude some types of defects. So if you want to exclude antisites or interstitials, you can also do that too. And it'll then output all these defect structures for your given initial bulk structure. So they do come with some PyMatGen proposed charge states, which are just based on the known oxidation states of the elements involved. So currently it kind of requires a bit of chemical intuition to rule out unreasonable charge states. So for example, here it's saying that it's created 5 different types of cadmium vacancies. So that's likely from -2 to +2 charge states. But you can rule out the positive charge states in this case. And so that's just something to keep in mind when using this as it is at the moment. And it'll also tell you kind of the multiplicity of these defects in your given structure. So in this case, this was a 64 atom supercell with 32 atoms being cadmium, 32 atoms being tellurium. So that's why there's 32 possible sites at which you can create a cadmium vacancy. Likewise for tellurium, can be the same for the substitutions. Then maybe more interesting for the interstitials, you can have, depending on whether it's creating an interstitial, let's say a tetrahedral hole or a different sort of site, you can have kind of a one possible interstitial cadmium site for every cadmium atom in the system, or in this case, 4 times as many possible or equivalent interstitial sites as there are cadmium atoms. And then using these Python objects where you have the defect structures, there are some other functions where you can generate all your input VASP files, where it'll give you kind of folders like this for each specific defect in a charge state. Okay, back to Joe.
Thanks, Sean. So now I'm going to talk about the in-car parameters that you need to basically get cracking with some of these calculations. So your real core in-car tags that you need in every defect calculation are, firstly, you want ISIF equal to 2 to ensure that your supercell maintains the same lattice parameters during relaxation across every single calculation, because you don't want your supercell changing size, but this still lets all of the atoms relax within. You want to turn symmetry off, because by introducing a defect, you've already broken the symmetry in your cell, and you also want this off for when you're calculating your host supercell energy as well, because the symmetry time-saving algorithms that VASP uses actually makes it a lot harder for the analysis software to recognize what's going on. So you want symmetry off for supercell relaxation as well. You're typically best off starting with Ibrion equals to 1, as it performs best when you're further away from a local minimum. And then as your defects get closer to relaxing, then you can switch to Ibrion equal to 2 if you get stuck. And for defects, POTIM equals 0.2 is generally a good starting point as well. The final core tag that you want on is iSpin equals 2, and this enables spin polarization. And this is really critical for when you're looking at different charge states and different numbers of electrons, because you need to assign the spin channels correctly. So this is another really, really important tag. The next tag that we will look at is LReal, and this accounts for basically how it's like another level of accuracy in the calculation. So for really big supercells or if you're not too worried about how much it costs, then if you're not too worried about how much it costs, then L real equals false will give you a more accurate energy, a slight increase in cost. Or if you've got a particularly large supercell, or you're not too worried about really, really accurate energies, then you can use L real equals auto, and then R opt equals this. So say you had 3 atoms in your 3 different species in your supercell, you would need 3 times this tag here. So this is a much faster frame for your calculation, but this L real equals false might be required if your relaxation is particularly tricky. Now some more fiddly tags. So if you're still not on the doped bandwagon and you're still doing your calculations by hand, or you're still using AID, which is like the predecessor to doped, then to enable the calculation of the post-processing corrections, you need to ensure that you have these 2 tags turned on. It's not too important which ICOR level tag you have on, but you should have it the same for each defect calculation in the project. If it's 0, it prints the average electrostatic potential at the core, and if it's 1, it prints the core state eigenenergies, and the potential alignment correction in AID will work using either. If you're using doped, which most people probably will be going forward, then you have some choice. If you want to use one correction scheme called the Fraser correction scheme, then the only one of those tags that you need to have on is LVHAR equals true. This creates a log.pop file, and all of the post-processing calculations are ripped from the log.pop file. And if you're using the Kumagaya correction scheme, then you want ICOR level equals 0, because all of the post-processing corrections are done from the outcome. And Sean will talk a little bit more about the differences between these in a short while. The final part of the in-car that I will discuss before handing back to Sean is what we do when we are setting different charge states for defects. So you've got 2 options here. One, you use doped, where it will read the POSCAR and POPCAR and assign charge states, as Sean was just discussing, using the PyMatGen core module. And this, you can then choose which ones you want to keep. If it's missed any, you can add them in manually. Or secondly, setting them up by hand, you have to use your chemical intuition to consider each defect site and change the amount of electrons and your electron spin accordingly. And this pops up again and again. You have to think about which defects are important and which are not. And it takes a little while to learn this. So if we consider the oxygen vacancy in indium oxide, we can work out the number of electrons at the defect site in the neutral charge state. We have oxygen in oxidation state -2. We then subtract the charge of the vacancy, which is 0, which gives us -2. So we have 2 electrons on the neutral oxygen vacancy. We can then ionize these 2 electrons off, as it's an N-type defect, donating them to the host to get the +1 and the +2 defect state, respectively. We can then consider the tags that we have to change in order to tell VASP that this is actually what we've done. And these 2 tags are N up down and N elect. So N up down sets the difference between the number of electrons in the spin up and spin down channels. And N elect sets the total number of electrons. We can calculate the number of electrons in the system by multiplying the number of each atom in the POSCAR by the number of valence electrons for that atom in the POPCAR, or you can just write a script to do that because it gets a bit tedious. So for a neutral oxygen vacancy, the number of electrons in your system is 378. We then note that we have an even number of electrons. 378 is even. So we have no unpaired electrons. So we can keep N up down at 0. For the +1 state, when we ionize the defects, we lose an electron. So we reduce N elect by 1. We now have an uneven amount of electrons. We have 1 unpaired electron, so we set N up down to 1. And then for the +2 state, we ionize another electron off, reduce it again, and back down to 0. You can then apply this logic to any defects, adding electrons if it's if it's a p-type defect, removing them if it's an n-type defect. Now, clearly, the fact that this is automated in doped is a massive time saver and can prevent a lot of errors when setting these charge states. But it is good to sort of understand what is happening in doped when setting these charge states up. And if you have a charge state that you don't expect, you can have a look in car and see what's going on. So yeah, we'll just use doped. So I will now hand back over to Sean to talk about correction schemes.
Thank you, Joe. Great. So, yeah, the point is defect calculations are expensive. And what I mean by expensive is the amount of computational power they require, which is, we kind of think about in terms of the product of the number of cores times the calculation time. So Dave Bowler in the UCL Department of Physics and self-acclaimed million atom man has a nice blog post on this for anyone who's curious. But the general point is that DFT calculations scale approximately cubically with respect to system size. So if you double the size of your unit cell, the calculation will take approximately 8 times as long with the same number of cores. In fact, this scaling is typically worse, sometimes closer to quartic scaling, I entered power 4 for hybrid density functional theory due to the inclusion of Hartree-Fock exchange in the calculation. So given that we have a finite amount of computational resources, especially in recent times, and that you don't want to be waiting months for your calculations to finish, it's important to ensure that you have the most efficient setup for your calculations. So the first thing to ensure you have a good picture of the convergence, or first thing is to ensure you have a good picture of the convergence behavior with respect to the plane wave energy cutoff, i.e. n-cut, and the k-point grid. So which can be tested relatively quickly with VASP up 2.0. And so the idea here is to make sure that your basis set is sufficiently accurate, but no more expensive than it needs to be. Okay. So one advantage when performing defect calculations is that the simulation system is by and large the same in each case, for intrinsic defects anyway, with the presence of different defects only being a relatively minor perturbation or difference to the overall cell. So what this means is that the optimal setup for one defect in your system should be the optimal setup for all defects in your system. And likewise, if one setup crashes for your system, the rest likely will too. So you can see the missing atom is that tin one in this case. So as such, I recommend to test a few computational setups using just one of your defect supercells at first, or just a bulk supercell is probably fine as well, to ensure that you have an efficient and importantly stable setup for your calculations. So the main things to check on this front are firstly ALGOS, this is your electronic minimization algorithm within VASP. So you want something which is stable. So often normal, so algo normal can sometimes crash with charge density mixing errors for hybrid. And then also something which is the most efficient. So these are the two main criteria in these cases. So something to keep in mind is that there have been, we've been doing tests on this tag for different versions of VASP, and the main takeaways at the moment are that algo damped seems to be typically the fastest per electronic step, but sometimes can be like fool's gold in that it also tends to need more steps to converge. VASP 6 has some hybrid speedup routines, which particularly help for algo normal calculations, and so this is definitely worth testing for your system if it's stable, as it can greatly speed up some of these calculations. You should also consider, as Joe mentioned earlier, different supercell size and point grid combinations. So it's generally accepted that a supercell larger than about 10 angstrom in each direction is typically big enough to avoid significant elastic or structural interactions between defects, and so that our charge correction schemes will account for the rest of the interdefect interactions. So this is another thing to consider when choosing your supercell dimensions. And finally, the k-point parallelization via k-par can also strongly affect the calculation speed. And so there are some tips on the wiki to help find an optimal value. So finally, another way that we can help the efficiency of our calculations is through this kind of technique of relaxation pre-convergence. So our general workflow for DFT calculations is for defects is to relax our defect structure and then calculate the formation energy of the defect in the relaxed geometry. So we can massively speed up these relaxations by using a pre-convergence strategy in which we start with the low-cost, slightly less accurate methods to bring us closer to our final structure without having to use the expensive high-accuracy setup until the very last part of the relaxation. So essentially, instead of having to do 100 ionic steps with a high-cost, high-accuracy setup that needs like 10 hours per step, we can do maybe 70 of these steps with a cheaper, rougher method that needs only 20 minutes per step, and then the next 20 with a more accurate method that needs maybe an hour per step, and then finally only the last 10 with our most accurate, most expensive setup. Just to give kind of a rough example. So typically the best way to do this is as follows. So firstly, we do a gamma point only calculation. So this is using the VASP GAM binary. And these are quite quick because by only including a single K point in the calculation, there are a lot of optimization routines built into this binary using the fact that we can do a lot more things in real space as opposed to reciprocal space, etc. So for a lot of defects, one other thing to consider is that there might be a few different configurations possible. So what I mean by that is different possible interstitial sites. So as you saw in the example earlier, there were 3 possible interstitial sites proposed for both cadmium and tellurium in the cadmium telluride supercell. And also you can have different magnetic configurations, but often some of these configurations can be ruled out quite early on as being very high energy, and so VASP GAM is quite useful for this in that we can quickly test a lot of the configurations and rule out some very unlikely or high energy defects from the start. So while the energies from this step are not quantitatively accurate, the relative energies are generally quite good qualitatively and can be used to determine the lowest energy configuration in these cases. Okay. So then using the relaxed structures from this first step, we can then increase our K points to our converged K point mesh. So the K point grid that we've decided to use for our supercell and that we're going to be using for our final energy calculation, and relax with the VASP standard binary, but in this case using the tag ncred, which allows us to undersample or basically use less K points for a specific part of the calculation in hybrid DFT, so that being the calculation of Hartree-Fock exchange, which is the kind of most expensive part of a hybrid DFT calculation. So the value you use has to divide into your K point grid, so it'll probably be either 2 or 3, and from this we from this calculation we then perform the final part of the relaxation with our full K point grid and no undersampling, which often only needs a couple of steps because this step turns out to be quite accurate usually. And then finally, we calculate the energy of our fully relaxed defect, for which you will need to use the VASP NCL binary if you are including spin-over coupling effect, so if there's heavy atoms present in your system. Okay. Yeah. Okay, back to Joe.
I think you got another. Are you going to talk about the stuff?
Oh, corrections and aids to me. Yes.
Yeah.
Sorry, yeah. That is the other way around. My bad. So still me, actually. Okay. And okay, so then once your defect calculations have finished, you can then post-process them with either AID or through Python. So AID by default uses the Lanny-Zunger correction scheme, and the input files kind of look like this. So firstly, you have the defects.dat file, where you manually input the information about your system. So starts with the host VBM and CBM eigenenergies, and then for each defect you give the symbol, the number of sites, the defect charge, whether it's P or N type, and then the folder with the final defect calculation, from which AID can parse the results and determine the charge correction, so the potential alignment and the defect point charge correction. In addition, you need to provide the chemical potentials in the chempots.dat file, the chosen chemical potential limits in your limits.dat file, and then also the dielectric tensor in the dial.dat file, which goes into the calculation of the image charge interactions. You then run the AID loader command, and it will parse the calculations and determine these finite size corrections. So as we're creating defects, we can also post-process them using Python as a possibly less painful approach. So again, different versions of this are implemented in different Python modules, but the three most popular charge corrections, so the Freiselt or FNV correction, Kumagain-Oba or Lanny-Zunger correction scheme, are all implemented in Doped. So again, with a few lines of code, you specify where your defect files are, tell Doped to parse them using the single defect parser function, and it will then store all the information about the defect, like the calculation info, the defect site in the supercell, the defect type and charge, etc., as well as computing these finite size corrections with your chosen correction scheme. And you can then get an output dictionary that tells you which corrections it has calculated and by how much, and then what your uncorrected and then corrected defect energies are. So as well as having as well as the advantages of having a reproducible record of your work. So if you run this via a Jupyter notebook, for example, there are two other particularly handy features of doing the corrections this way, in my opinion. So firstly, you can quickly look at the charge correction plots. So like this one for the FNV or Freiselt scheme, to check that the corrections look reasonable. So in this case, the green line here is the kind of long-range Coulomb potential from the Freiselt model. So this is the kind of the Coulomb potential from your charge defect that would be predicted if it was just a kind of single Gaussian charge distribution. And then the red line is the difference in the electrostatic potential in your defect supercell relative to your bulk supercell. And so then by subtracting these from each other, you get this blue line, which is essentially how the Freiselt scheme works to determine the charge correction. And so what you want is a plateau region here, which corresponds to the edge of the supercell, and you see this is where it samples the blue line to determine the charge corrections. And so from this, you can kind of determine if basically if it's reasonable or if there's seems to be kind of a bit of variation still happening even at the edge of the supercell. So the plots for the other charge corrections like the Kumagai and Oba scheme are a bit different, but the general idea is the same, where you want this kind of plateau region at the edge of the supercell. So additionally, doped will throw up warnings in cases where the charge corrections are likely to be inaccurate or inappropriate. For example, if you have a large number of electrons or holes occupying the band edge states, the band filling correction is likely inaccurate due to gap renormalization, and doped will throw up a warning about this. And also, if it detects significant variance in the sampling region for the charge correction plots, it'll also throw up a warning. So this can be quite handy to avoid errors which might otherwise be missed. Yeah, so it's definitely on to Joe now.
Sure. So I'm now going to talk about something that a few people have been asking about in the last month or two, which is how to account for polarons when doing defects. So a polaron is a quasi-particle used to describe what happens when a charge carrier interacts with ions in a system. And this results in a bound state. And that sort of definition sounds like quite buzzwordy. An example, we can sort of imagine what's happening. So you can picture like an electron moving through a crystal, and it will interact electrostatically with the positively charged ions in the crystal. These ions distort slightly in order to screen this electric charge, and this interaction will slow down the electron. It now has this interaction with the ions around it associated with it, and this increases the effective mass of an electron and reduces its mobility, and there's an interaction between them, and this interaction is the bound state. So for this electron to then carry on moving through the lattice, it will need a sort of energy to escape this localized binding and then to move on. So these sort of type of defects will typically have activation energies. And you can sort of extend this same logic to holes as well, so positive holes rather than electrons. So if you remove an electron, creating a hole, this region of positive charge can then get trapped by any surrounding negative ions. And this is quite prevalent in systems that are highly ionic and polar. And so we need to account for this in these sort of materials. And one classic culprit is the oxides. So again, yes, this requires us to use some chemical intuition. And there's a wiki page talking through this, but I'm going to talk through an example now. So we're going to stick with indium oxide and this time look at the indium vacancy. So in a neutral indium vacancy, we would expect 3 holes, and then we can accept 3 electrons, which is each charge state. So we can have 1 electron in 2 holes, 2 electrons in 1 holes, or 3 electrons in no holes. And it is a p-type acceptor defect because it's accepting these electrons. We can now go through how to set up a calculation accounting for polaric behavior in each of these charge states, and then see the end results and how this affects the energies and the localized charge. So if we take the neutral defect where we have 3 holes, we can imagine them to sit in different spin arrangements. So we can have all 3 holes in the spin up channel, or we can have 2 in the spin up and 1 in the spin down. We can control this in VASP by using the magnon tag. So this will set an initial magnetic moment on the atom at which you specify it. So this can allow us to assign these holes into spin up or spin down. So in indium oxide, with an indium vacancy, this is what our postcard looks like. So we have 31 indium atoms and then 48 oxygen atoms. And this is important for looking how the magnon tag plays in a second. So we have 381 electrons in our system with an indium vacancy. And then we can consider the all spin-up arrangement. So we have n up down is 3 because we have 3 in the spin-up channel. And then to assign magnon to this, we have 31 times 0, so there's no magmum on the 31 indium atoms. There's then no magmum on the first 45 oxygen atoms. And then there is a magmum of 1 on each of the final 3 oxygen atoms. And this will assign a magnetic moment to those final 3 atoms. These final 3 atomic coordinates in this postcard are actually the 3 oxygen atoms that surround the vacancy. So it's important to make sure that you're actually assigning these magnetic moments to the atoms that surround your defect rather than just any random defects at all, any random atoms at all. And this is something that's currently being worked on to be implemented into DOPE, so you don't have to mess around with this too manually. We can then consider the other case where you have 2 spin up and 1 spin down. So overall, you only have 1 electron in a different spin channel, so our N up down is 1. And then to assign the magnetic moments to this, it's a similar sort of process, but now we have 2 in the spin up and 1 in the spin down. You can then test the energy of both configurations with gamma 111, like Sean said earlier, just using a cheaper calculation, and then whichever is lowest energy you can move forward with. We can apply a similar process for each charge state. So in the case where you have 2 holes, you can either have them both spin up or you can have them spin paired. And this then changes how you would, it gives you, again, 2 different cases on how you would set up your calculation. And then the same for the final hole, you can just have the 1 option. So you would, again, increase your N elect and then just have N up down is 1, assign 1 magnetic moment. And for the final case where you have no holes, you don't need to do this at all, because you don't need to include magma because you've got no holes to consider. So what does this actually look like in practice? Well, what we have here is the whole charge density plotted for each case. So here we have the neutral vacancy with 3 holes. The vacancy is in the middle here, and then on each of these oxygen atoms surrounding the vacancy, we have 1 hole, 1 hole, 1 hole. As we introduce an electron, we lose a hole, which is what happens in this case, and then another electron, and then there are no holes in the final case. So you might think, does VASP just do this on its own? Why do we have to input this manually? Well, if you let VASP try and do its thing, it gets it wrong. So this is the case, again, where we've specified the magmum. This is the case where we haven't. And you can see that in the same charge state, VASP will on its own relax to a higher energy structure with a split hole rather than correctly localizing the charge. So this is why you have to be careful about actually assigning your magnetic moments rather than just letting VASP do its thing. And again, like I said, this is particularly relevant when looking at oxides and highly ionic systems. So to summarize, you need to consider the ionicity of the material. This is less likely in materials with more dispersed valence band maximums that aren't dominated by, say, oxygen. You want to test all of the combinations with a gamma point only calculation and then proceed with the lowest energy one. And you can then visualize these whole charge densities using the par charge file. If you're expecting localized electrons, you can apply a reverse sort logic as well. But VASP is typically a bit better at localizing electrons than it is at holes. The final thing I'm going to look at and talk about is, well, last time we discussed how to calculate chemical potentials for simple binary systems. But as we know, everyone seems to work on more complicated ternary, quaternary, quinary systems. So I thought I would quickly discuss how to do that for those as well. So we need to calculate the values of mu I for each element in a complex chemical potential space. And I'll run through how to do this with barium understanding. So we can use the code Kaplat, which is developed by John Buckridge, who's an alumnus of the group. And we can use the usual steps. So we calculate our elemental reference energies. We calculate the formation energies of all our stable repeating phases, again, in energy per formula unit. And then we simply run Kaplat. So a sample input file looks like this, where in the first line, we specify the number of species in the host compound, so 3. In the second line, we put our stoichiometry and formation energy in this specific format. So 1 barium, 1 tin, 3 oxygens, and the formation energy. We then set a dependent variable, which in this case I've set to be none of them. We then put the number of competing phases, which is 3, and then we put the number of species and the stoichiometry and formation energy for each competing phase, as we did up here. And there's a sample input file when you download the code as well, where you can run through this. So once you've run this, Kaplat then solves the simultaneous equations that you would create with all of these competing faces, and it tells you at which point these points intersect in the chemical potential space. And we can see here that when we have a really, really low oxygen chemical potential, this represents our O4 limit, and where we have oxygen-rich conditions, this is our O-rich limit. We can then visualize these using a 3D XYZ plot or a 2D XY plot with a color bar. And to do that, you would need to then set a dependent variable. Or if you've got a higher order system, you can then do a 3D XYZ plot with a color bar. There's loads of different ways to do this. Here are some examples. So again, this is for the binary. Like last time, we just plotted X against Y. For a ternary, we can plot X against Y and then include the third chemical potential as a color bar. And then for a quaternary material, we can set 1 as constant and then calculate the 3 in an X, Y, and Z plot like that. We can vary the fourth one going across. So there's loads of different ways to do it, but all you need to do is identify the 2 extreme limits and then use these as your chemical potentials for your defect calculations going forward. So I'll just hand back to Sean now to wrap up.
Okay, great, thanks, Joe. So some general tips on optimizing chemical potential calculations. So often some of your chemical potential calculations for elemental and or competing phases will involve metals. And unfortunately, these usually require a very dense K-point mesh due to the strong dependence of system energies on the Fermi surface. One way in which this behavior can be improved is by switching to tetrahedron smearing, so I smear -5, which typically results in kind of a better and faster convergence with respect to K-point mesh, as opposed to Gaussian smearing or Met-Fessel-Plaxton smearing, which is I smear 1 or I smear 2. And also depends much less, or doesn't really depend much at all on the choice of smearing width, so your choice of sigma in the INCAR. Given the cubic scaling of DFT, it may not look like much here, the difference between, say, a 12 by 12 by 12 K-point mesh as opposed to 16 by 16 by 16, but it greatly reduces the calculation cost in these cases. Provided you have a well-converged K-point mesh using ncred equal to 2, typically does not significantly affect the accuracy of the calculated energies, and also reduces the calculation cost by about an order of magnitude. And as I said, tetrahedron smearing often permits a reduced K-point mesh in the first place. So these are something to keep in mind, particularly for the chemical potential calculations for metallic phases. So the main result from processing these calculations is the famed defect transition level diagram, which provides a huge amount of information about the thermodynamic defect behavior in the system, some of which was discussed in the last defects tutorial. So the one component of this that we haven't discussed, discuss the chemical potentials, ignore that. So depending on the scope of your investigations, you may want to take a closer look at the particular defects which are most relevant perhaps to your investigations. So likely the low energy, high concentration ones. So these ones down here, which will be most prevalent in your system, or perhaps deep defects that are inhibiting solar cell performance in the system, for example. So just to mention some of the ways that this can be done, to take kind of a closer look or in-depth defect analysis for particular defects or charge states in your system. So firstly, would be structure visualization. So just by looking at the output, relaxed structures in Vesta or Crystal Maker. You can look at the electronic density of states via Sumo DOS plot. So to give something like this, for example, where you can look at the defect related states, maybe within the band gap, or if they hybridize with the band edges. And or just by looking through the eigenval and procar files, which also give you this information. from the transition level position, as we mentioned in the previous defects tutorial. You can get a lot of information from that on the kind of predicted defect behavior, i.e. is it deep, shallow, or resonant. You can look at charge or magnetization density isosurfaces, so like the ones Joe showed earlier for the polarons in the system, and you can get these from either the charge car or the part charge files, depending on if you're looking at total densities or densities for a specific states. You get figures like this. You can look at the structure and bond length analysis. So through Vesta, you can also do this with doped or PyMatGen to kind of analyze some of the relaxations involved with your specific defects. And finally, the crystal orbital Hamiltonian population, so the COHP, which is something that can be done through Lobster, where you can look at the bonding behavior. So if certain types of states are more bonding or anti-bonding, like, for example. Finally, to conclude, we'll just give a reminder of the steps we've gone through. So we start with our relaxed primitive cell, from which we calculate the dielectric constant and construct our defect supercells, which we then relax and calculate the total energies. At the same time, we relax and calculate the energies of our elemental and competing phases, from which we determine the chemical potential limits. Feeding these results into our post-processor, so whether age, doped, or elsewise, we apply the finite size corrections and construct our transition level diagram. And then we use this to analyze the defect behavior in the system, likely taking a closer look at defects which are particularly relevant to the overall system behavior. So on that note, thank you all for your time and attention.